Part 2 of what is walking, what is legged locomotion. Okay, so we talked about taking a step with a simple point mass model, and we talked about changing the height and showed that that won't stabilize. That doesn't allow for stabilizing straight up. Next we'll talk about what a foot gives you. So let's go back to the model then where we have point mass at a known height trajectory and point foot, or sorry, not a point foot now. So now we'll have it so that we have a finite size foot and stay in 2D for the time being. And let's make it so that, I don't know, so that the middle of the foot is defined as x equals 0. Okay. So here we have our typical phase space, again, x versus x dot. These are capture trajectories, they're stable. And let's draw it first for when the center pressure is in the middle of the foot. These are unstable ones. And then you have your saddle point behavior. Okay. So we've been saying that with a point foot and a point mass, the force has to lie along the line between the point foot and the point mass. And the length of it will depend on gravity and your z-path or whatever, but it always has to be in that line. When you have a foot, that gives you the opportunity to change where your center pressure is, thereby changing the direction that your force is applied. Right? Put it on your toes or on your heel. Okay. And with this simple model of everything, changing where your foot is, changing where your center of pressure is, which you can do, assuming you can do it instantaneously just by changing torques on the ground, is kind of the same as making your point foot move to that point instantaneously. Right?
So you have a small amount of continuous slide that you can do to the phase space chart.
Yep. So let's say this was one edge for a foot right there, and this is the other edge. If we put our center of pressure on our toes, then the trajectories we would get at this point instead of, so normally we would get this if the center of pressure is right in the middle. But by putting our center of pressure right at that point, that now becomes the location of where these trajectories come in. Okay. Okay. Or if we put the point at the heel, same thing. Hopefully this won't clutter this too much. But you can shift the center. You can shift the fixed point, shift the fixed saddle point, left and right. So pretty much take all your dynamics, shift it forward to the front of your foot, or shift it back to the back of your foot. Which then, if you're talking about like capture trajectories, it gives you this whole swath. So this point here would be center mass directly on top of your toes. This point back here would be center mass directly above your heel. And the point in the middle would be center mass halfway above. Okay, so you can come to a stop on, on your weight in front of your toes, weight on your heels, or weight in the middle. And so that gives you this entire swath of capture trajectories.
Does the diamond correspond to stabilization of the
Yeah.
point?
Well, this really anywhere in here, you can come to a stop. This diamond doesn't really mean much. It's really these two lines that mean what's stabilizable.
Okay.
And since the origin is now fully encompassed, it's stable, which is obvious, right? If you got a foot, you can stabilize on top of it. Okay. So if you're walking along and you find yourself, you know, find yourself here and you take the step to there. If you're back here, then you might have to keep your weight on your heels for a little bit until you get pushed forward, and now you can put the weight on your front of your foot and get to there. Okay, anything else to say about that? Okay, but with this simple model though, again, it doesn't matter what the mechanism is from here to here. Or should we run it from the ankle to here. Doesn't matter what the mechanism is. As long as this is a point mass, the force has to lie along the line from the center of pressure to the point mass. Okay, but you see you get this stabilizing effect, and this distance of stability is the size of the foot. From here to here, this distance is the length of the foot. And really, and that's going to be the case, is that true? Yeah, anywhere out here it's going to be the length of the foot. So these curves will just follow this one in. So if this is yours, stable capture trajectory. And these will also be where this is the length of the foot. Make sense? Good. So we're still managing to have very few equations. Keep doing this intuitively using phase portraits. All right. So now the next thing we're going to do is add internal momentum. So erase this so I can redraw it. Okay, so let's go back to a point foot, just to keep it simple. So again, point mass, or sorry, not point mass this time, point foot, but instead of a point mass, we have something with mass and inertia. Okay. All right, so what does that give us? Suppose we can, let's right now model the inertia just as a flywheel that's centered about the center of mass, just for simplicity's sake. What does it provide us? Yep.
It provides us, instead of a radial from the center of pressure to the point mass, it also gives us the possibility of tangential.
Yep. So instead of the force having to lie along the line from the center of pressure to the point mass, it can also have a tangential component to it, which we can, I guess, write by having
Right angles there, right?
something that's not, oh, we not draw it straight up.
It could have a component at right angles and the resultant could deviate.
Yeah.
That's correct.
So let's make the resultant be like this. Okay. So if that's the ground reaction force, we're drawing the center mass there. Okay. So the angle is going to change, which has two effects. One is that the x component of the force, assuming the z component is the same, now the x component is going to be different. And the other effect it's going to have is torque about that mass. So as it's drawn this way, it would cause this mass to accelerate in this direction, or this inertia to accelerate in that direction.
We could consider that both the radial and the tangential will have both x and z components.
Sure.
Yeah.
Works. Okay. All right. So this will cause the flywheel to start accelerating in that direction, but it allows us to change the angle. So no longer are we completely limited to having the angle of the force be along that line, which means before we had written that the sine of x double dot equals the sine of x. That's no longer true, right? Well, let me kind of write when it is true and when it isn't. So that's going to be true if the angular momentum, let's call the angular momentum h, when h dot equals 0, then the sine of x double dot will equal the sine of x, and we'll have the same dynamics we've had for the last few boards here. When h dot doesn't equal 0, then the sine of x double dot might not equal the sine of x. Let's see here. I guess the way you'd write it is when it doesn't equal that, that implies that. But not necessarily the other way around. But anyway, so let's draw the draw the phase portrait again. Okay, so first I'll draw it without using any momentum. So we got the unstable ones. X dot. Capture trajectories. Okay, so there's a bunch of different ways of looking at this. One is that we now just introduced another variable. So we had x, x dot, z, and z dot, though by constraining it on f, z equals f of x, then we got rid of z and z dot. But now we have theta and theta dot of the flywheel. So really we're back to 4 dimensions, or 4 state variables, which means that we can kind of, that this is a 4-dimensional space, so we can go into the board and out of the board, and we're no longer constrained to not being crossing paths and whatnot. That's one way of looking at it. Let's see here. But another way is, let's look back at this picture again. And let's see here. If we were to take the actual force on the mass, so this one, that's, and project it down to the ground here, and find this point. This is kind of like the point that the force, not the torque, that just the force component is emanating from. This is the centroidal moment pivot. Centroidal moment pivot. Okay. So this point, when h dot equals 0, that means that the COP equals the CMP. Center of pressure equals centroidal moment pivot when you're not accelerating the mass. They're right on top of each other. When h dot doesn't equal 0, then the COP doesn't equal the CMP. Okay? So it allows us to change x double dot a little bit. So if we look back at these phase portraits, any point on this phase portrait is going to have kind of a vector showing what x dot is, x dot versus x double dot, right? It's kind of what defines the angle, the tangents for these lines. So what moving a flywheel around and moving the CMP allows you to do is allows you to get a little bit more or less x double dot. So we could go a little bit more at this point or a little bit less. So it kind of gives us this area to work in now. But we can't change this component because it's just x dot, it's our state vector. But x double dot we can change by throwing around momentum. So every single point on this graph now, if you look at the vector field, now you can open it up a little bit, and these are your options.
Now you have to pay for that later by accelerating the mass in the other direction.
Exactly.
It allows you to ride a different curve for a little while, which might separate from the rest of the curve, so that when you shift back, you end up in a different spot.
Right. So in order to pay it back, what you typically do is overcompensate for what you want to do, and that gives you more effect, so that you do the opposite to unspin your flywheel essentially.
But you want to make sure that it occurs in such a way that it diverges.
Yeah.
Because if it's converging, then you'll just end up with rotational inertia that you have trouble with shedding later on.
Exactly. So let's go over that example. So suppose we're straight up and down, and somebody gives us
pre-allocate.
What's that?
I suppose if it's converging, you could pre-allocate for a point later on. So you could get some angular momentum that you plan to use later.
Yeah, but you do have to take it into consideration.
Yes.
Either. Yeah. So let's just do a simple example. You're straight up and down, so x, you're right there. X equals 0, x dot equals 0. Somebody gives you a push. So now you have a velocity, but you're still straight up and down. So that's right here, right? If you were to do nothing about it, you would start just falling forward up to infinity, which would be this curve here, right? But now we said we can open up these curves by doing our momentum, and we want to get back to here. So instead of going that direction, let's go this direction at this point a little bit. And then kind of keep doing that. Let's see, keep doing that. So now at this point, instead of going that direction, we can go that direction. And then kind of keep working ourselves
to the
around.
left to come home, right?
Yeah, we need to do a kind of a hard curl.
To the left.
No, this
Because
one.
we need to get into this stabilizing quadrant on the left.
No, we'll end up getting in this one.
Okay.
So what you want to do is, suppose could you go either way? No, because any point up here has to be going that direction because x dot is positive. So we can't go this way.
Okay. Okay.
So we spin around in here. Until we kind of do this sort of thing. And for the first portion of it, till some point out here, where we're accelerating one direction, so h dot is greater than 0. And then for the other portion, we're paying it back. We're coming to a stop, so we need a h dot is less than 0. And of course, you could speed up, slow down, but given the constraints on what you can do with the flywheel, the optimal is going to be to just immediately start lunging as hard as you can until the point where you can immediately start braking as hard as you can and come into that point. So again, since it's 4 state variables, what's really happening is z and z dot are out of the plane. And you're kind of going into z dot, looping around, going to negatives. Negatives, z dot is negative here, z dot is positive there. Or sorry, not z. Theta dot is positive on one, negative on the other. And coming to us.
So we could define a critical damping or a deadbeat response within torque limit constraints.
Yep, and we have done that, but we're not going to do that now.
Okay.
But let's do a demonstration. Need a volunteer. 2 volunteers. Nick and
It's
John.
probably going to involve falling.
Okay, Nick and John. Johnny, stand here facing that way.
Okay.
Back up a step. Okay, Nick and push randomly. And Johnny, don't take a step. Okay. Notice which way did you launch? Forward. Okay.
Right, to try to fight that.
All right, so you can have a seat. So let's look at that case. So Johnny is standing here. Here's a simplified model of Johnny. And Nick gave him a push to give him velocity that way, and he started rotating this direction.
Correct.
Okay. Because he needed a force in that direction to slow himself down. So the ground reaction force was that way instead of straight up. And you can see how that has a torque that would accelerate the mass that way. So that's one way of looking at it, is ground reaction forces having a lever arm with rotating mass. Another way of looking at it is you've got a pivot here at your center of pressure. So about this point, angular momentum is conserved. The only thing that will change it is gravity. Let's forget about gravity in this situation. by accelerating something this way, that gives a angular momentum that way. But since angular momentum is conserved about that point, something had to be accelerating that way, which is the center of mass accelerating backwards. So the net acceleration at about this point is 0.
So if I lunge forward, my
total
foot
H
could
dot
slide forward.
About the center pressure.
And that means the ground reaction force is
So
acting against
0
when my
on
foot
gravity.
slides.
Okay, so that makes sense? Okay. Okay. So so another way of looking at angular momentum, much like the foot, it essentially increases. It's essentially like increasing the size of your foot because it allows you to put your centroidal moment pivot outside your foot for a brief period of time, right? But unlike a foot where you can do that continuously, you eventually have to stop doing that or your flywheel will keep accelerating. Now you could, if you didn't have any limits on your flywheel, you could do the situation where you're just leaning forward and let's see, I guess this was the same as Johnny's case here, so just making it go
Continue to
faster
ramp
and
the
faster
velocity.
and faster. Yeah, just keep ramping up the velocity and just hover out there.
Right, so this is our throttle angle for driving a hex wheel. To maintain an angle, just
But we're
keep accelerating.
talking about
Same thing though.
Yeah, we're not talking about hex wheels right now.
Right.
Let's keep it simple.
Okay.
Okay.
It requires acceleration, not just velocity, right?
Velocity ramping is acceleration because the velocity is increasing. You're absolutely correct.
Okay, so there's that. All right, so let's just review here. Okay, so your balance mechanisms. Are taking a step. Moving your center of pressure. And essentially these are really the same thing because taking a step means moving your center of pressure a large distance. Using accelerating internal momentum. And your center mass height trajectory. And for most legged systems, humans, humanoid robots, whatever, it's pretty much in this order. Taking a step gives you, let's call that 4 stars. Moving center of pressure is only 3 because you can only do it a limited amount. Accelerating internal momentum, for most parameters we use, it turns out that the amount of benefit you get is the same as, as the size of your foot, essentially. But since you have to pay it back, only give it 2 stars. And center mass height trajectory doesn't do really much for you. Only give it 1 star. Where it does do a lot for walking is toe off at the end of stride. So let's see here. When you're in this situation where when your center of mass is way in front of your foot. And you toe off. It gives you more benefit at this point because of this angle. You're getting much more FX for a given FZ, right? Whereas if you change your center of mass trajectory when you're right above your foot, it doesn't really do anything for FX, for your forward velocity. So it's best either at the end of your stride when you do a big toe off, or at the beginning, like with the long jump example, if you let your body go low when you first land.
Do you actually need to increase your height there in order to get the benefit? If you just allow if you keep Z the same but keep your foot on the ground longer by extending your leg with the toe off, you get a similar
Right.
result.
Well, what that's essentially doing though is it's keeping your center of pressure back longer. right?
Okay.
By changing your timing of when you take a step and when you change from double support to single support, that's essentially controlling your center of pressure to just be somewhere for a longer amount of time.
Okay.
So I guess that's another one, is just the timing of all this stuff.
So I think Nick's question is an interesting one. If we were constrained to keep the center of mass moving horizontally, we'd have to extend the radial distance between the point mass and the COP, right? Or even the CMP.
Mm-hmm.
But moving up does more for us, does less for us? These are various strategies. So is there a difference that needs to be made there?
Can you say the question again?
So is there a extra benefit to using the toe off at the end and actually raising your center of mass as opposed to just keeping Z?
Oh, right. You can
consistent?
use it for two things. You can, by just lengthening your leg, it allows you to stay longer, so then you got a deeper angle. Right?
Yeah, so you get more angle that way.
Right, so you can either just stay longer or do that and give a little bit of toe off.
But I think the benefit to using that toe off at the end is that you can have your overall Z through the majority of your stride be lower, and still have the get back up to where it started, so you can get to the next one by increasing it slightly at the very end.
Yeah. Okay, so what's going to be next up is, so notice, I think I had two equations that were very simple, some fairly complicated phase portraits, but on purpose I kept this one as intuitive as I could, kind of staying with the fundamentals of what's going on, to show that these are the four things you can really do. Maybe there's a fifth we're missing, but these are the big four. So next we'll do the, next lecture would actually put equations underneath everything and keep it simple and do the linear inverted pendulum. Oh, so that's next up.